When I was in my last couple of years in college, I learned a few things that might be applicable to the topic I'm going to give today. The main objective here is to show that or to sketch 16 issues that are mostly scientific and to claim that the evolutionist responses fall short. These are the conventional responses that you might see in periodicals, in the news media, who knows what. One of the things that I learned during those last few years is that there are 4 philosophical schools of thought. I learned that in my History of American Education class. And keep them in mind because when you'd like to ask the question, how do I know something is true, you'll be referring to one of those 4 schools. The first one is the absolutist school, which means that somebody told you that something's true. The second is the empirical, which means somebody tested it. The third is the pragmatic, which is somebody said that it showed that it worked. And the fourth is the existential, which means somebody showed that it occurred. The preferred choice that I'm going to be focusing on this morning is empiricism, and that would be the one where we're testing, correlating, cross-correlating, always in the questioning eye of the skeptic. Here are a few lines from a well-known cartoon, this is the one where Christopher Columbus is trying to convince Ferdinand and Isabella that the world is round. Maybe you recognize some of those lines. It's a dialogue between them. She's a round and she's a flat, and so forth like that. We all have our different perspectives when we come to the table, and they certainly did in that cartoon if you ever see it. Empiricism I call the dispassionate interchange. This involves things like the scientific method. We compare our model or theory versus reality. That's the pragmatic aspect. We collect, measure, observe, test, correlate, cross-correlate. In other words, using the 5 senses. And we're always in the ever-present questioning eye of the skeptic because we really want somebody to be able to check to see that we're not missing something or that we haven't made a mistake in what we're doing. And so we need an adversary. Sometimes this is also called falsification. You need a test of falsification to show that something could be rendered false if in fact there were something wrong with the theory. Rather than saying, well, it's above reproach, there's nothing that could even assail it. And the best we can do in empiricism is to say that we have probabilities. We could either have a very low probability or very high probability or some probability in the middle. There's no such thing as an absolute 0 or an absolute 100% in empiricism. You might want to go to another school of thought if you wanted to get 100% or 0. Also, we modify our conclusions based upon new information, new testing procedures, anything that comes in that we were not aware of before or were made enlightened to. If you've ever heard the tale of the blind man and the elephant, you might recognize these lines, especially the last one that goes, each was partly in the right and all were in the wrong. And so often we come to the table with our own perspectives. We're not aware of other people's perspectives, and we're sometimes not even fully aware of our own perspectives. And so we will be forever looking in that event. And so this is another reason why we need to bring all the data that we can to the table instead of leaving some of it out. The general principle I wanted to say is that verified scientific principles don't displace other verified scientific principles. What often happens in the media is we'll see somebody coming up with a brand new theory, and what they'll never do is come back to the old stuff that we do know is true and compare it against it. Instead, we're led to believe that the new scientific theories have suddenly displaced the ones that we came to know and love, and somehow we have to get on the bandwagon. We have to be up and with it. Not so fast as Stephen Wolfram found out at Caltech, and I was there to see this on February 1, 2003, when 3 skeptical scientists at his old alma mater said to him that the new science better agree with the old science. We're going to see this show up again and again. Here's another line you might recognize or two. These come from Miracle on 34th Street. You've heard of the French nation, the British nation. Well, this is the imagination. And that's not how it really works in the scientific laboratory, but it's just as well as far as the public is concerned sometimes. Or I have great respect for science, and I have great contempt for amateurs, sometimes said to be meddling amateurs who go about practicing it. Those were spoken by the Santa Claus character, if you ever see the film. Here's something else we have to keep in mind. There are two words that often show up in these dialogues. One of them is interpolation, and the other is extrapolation. Does anybody know what interpolation is? Can somebody define that for me? Anybody? Yes.
You're talking about interpolation?
Interpolation, how would you define it?
You go between 2 points and try to figure out what one of the midpoints is.
Right, we're trying to fill in the middle, and it's to put things in the middle, to interpolate. What about extrapolation? What does that mean? Somebody else? Anybody else? Does anybody know what extrapolation means? Yes.
On a curve, if you have a trending line going beyond the point, there is no point beyond.
That's right. Now, I'd like to point out this quote from Wikipedia. Extrapolation is similar to interpolation, which produces estimates between known observations, but is subject to greater uncertainty and a higher risk of producing meaningless results. Now, there's no such thing as either a universal interpolation method or a universal extrapolation method. But of those two, I'm going to go with interpolation if I can. It's especially subject to mischief, extrapolation is, when going back into the unobservable past, which is so often the case. Were you there to see it? No. Were other things there to see it? Maybe not. Now, who comes to the table to try to explain scientific principles? Well, nowadays, creationists, evolutionists, whoever. And one of the things that is commonplace for evolutionists to do is to say they have a stake in a whole bunch of matters, not just the gradual changes of species or whatever. Otherwise, they might have some window in to allow God in the door, whatever. So evolution, by the way, just means change. But they're interested not in just biological at the bottom, but also in chemical, stellar nucleosynthesis, molecular abiogenesis, cosmological, stellar nurseries, galaxy formation, language, societal. The term evolution has come to mean a lot of different things. And as such, some of the things that I've posed are, in fact, a number of things I've posed are not strictly in the biological category because of the fact that evolution could mean a number of different things. See this going on. I need to review something called thermodynamics. Does anybody have a background in chemistry and physics? Has anybody seen anything with thermodynamics? Anybody at all? Anybody? Yeah, I knew you'd be there. Anybody else? Yeah? How about Ken? Yeah, you've seen some of this stuff, haven't you? Thermodynamics? Does that ring a bell? Thermodynamics? Yeah, sure. There are how many laws of thermodynamics? 3 or 4, depending on how you count them. Let's go through them. The first law says that there's conservation of energy or mass. That is, mass and energy is neither created nor destroyed. Some way I can put it this way: you can't win. The best you can do is break even. The second law is that the usefulness of that energy is continually deteriorating, or in other words, entropy is increasing. Or some way I put it, you can only break even at absolute zero. And the third law just kind of speaks for itself. You can't reach absolute zero. And there's a zeroth law that says that you must play the game. And therefore the conclusion is you must lose. This is what life is like under the sun, if we might say that in Ecclesiastes. You must lose. Sir Arthur Eddington put it very well in 1922 when he said that entropy is time's arrow. That, by the way, is featured in section 2 of chapter 8 of this book, Gordon Barrow's Physical Chemistry. Here are 16 issues then. Why does anything exist? Number one. Number two, did the universe always exist? Number three, did the universe cause itself to exist? Number four, how can the universe avoid heat death? Number five, how can anything travel faster than the speed of light? Number six, what is the origin, transportation, and distribution of carbon? Number seven, how do any stars exist? Number eight, how do moons form? Number nine, what is the ongoing source of long-term comets? Number 10, how do any elements heavier than iron exist? Number 11, how do peptide bonds exist? Number 12, how do proteins have only L, in other words, left-handed amino acids? 13, what turned non-life into life? 14, how does metamorphosis occur? Insect metamorphosis, I'll mention. 15, how do major morphological changes occur? 16, what creates information from gibberish? Now, every one of these topics, of course, could fill many libraries, so I'm going to be actually covering just maybe one or two or three at most aspects, which you might be able to take away with you and use. First one, why does anything exist? I would propose to you that topic, number one, in this book, Roset's Pocket Thesaurus. Want to take any guesses what topic number one is? Any guesses? Existence. Now, Roget's Pocket Thesaurus is about the most neutral reference source I can think of, next to a dictionary. It's more than a treasury of synonyms and antonyms. There's much more to be said than just that. We'll get to that in a moment. Because we can find a lot about the structure of the language just by examining the structure of the contents in this book. If topic number one is existence, it stands to reason that the topics at the end of the thesaurus deal with the possible causes of existence. And of course, you might know what I imagine the cause to be. Other than that, if nothing exists, no space, no material, no people, no meaning, nothing. From nothing, nothing comes. Not only do we have to ask a question which the evolutionists have no real way of attacking in the first place, why does anything exist, but why this particular amount of material? It's been estimated we have about 10 to the 80th atoms in the universe. Why not 10 to the 79th? Why not 10 to the 81st? And why is it distributed the way it is? Throughout the universe or in the solar system? There are no particular answers they have to give to any of these kinds of questions. In fact, they really don't even like to raise the questions because, of course, they are unanswerable in their paradigm. Also, I need to say something about something called quantum fluctuations. This is I don't know if you're familiar with quantum fluctuations, but quantum fluctuations is the theory these days that says that you can start with essentially nothing, and you can form a particle and an antiparticle, which can come back to nothing and go back and forth between that. And this is how the universe could have started from nothing. Is that true? No. Why? Because a particle and an antiparticle, if they ever do come together, annihilate each other, forming energy. If you continued that process over and over again, you could make unlimited amounts of energy from nothing. This is a violation of that first law of thermodynamics, that is that the mass energy of the universe is constant. It doesn't increase and it doesn't decrease. This would violate that notion. What is it that is really proposed? Not that nothing produces a particle and an antiparticle, but that there is an already existing energy field that produces them. And then these particles can come back together. The problem, of course, they would have is explaining where the energy field came from in the first place. Two, did the universe always exist? No. Because if it did, we wouldn't be here. Everything would have already dissipated according to the second law of thermodynamics. That is, that energy is becoming less and less useful. There's more and more disorder. This leaves a problem for the evolutionist. Either the universe is open or it's closed. If the universe is open, which is what they continually suggest, then that would allow other entities, maybe even a creator, into the door. Okay, so they can't have that, so it has to be closed. Well, then if it's closed, then they're subject to the laws of thermodynamics, and there will be energy death, which we'll mention in a few moments. So they're had either way. Did the universe cause itself to exist? Since it didn't always exist. No, because if it did always, because if the universe caused itself to exist, then it would have had to have existed before it existed to cause itself to exist. This is a logical problem. Or you could say the universe would have had to have existed and not exist at the same time and in the same way. That would be making A and not A true at the same time. This is not even logical. We can put those first three issues to work right now to show what is called the cosmological argument. I say in two-question form. The first thing is, did the universe always exist? Does the universe exist? We can say affirmatively, yes, it does exist. Did it always exist? No. Did it cause itself to exist? No. So therefore, the universe has no material cause. I've just ruled out all material causes because everything else is a subset of those questions. So therefore, we only have two possibilities. Either there is no cause, in which case you're an Eastern mystic, the conversation ends, because it's not scientific anymore. Or there still is a cause, but it must be immaterial. Choose from the following list of possible immaterial causes. Fairies, leprechauns, gnomes, my favorite, flying spaghetti monster, God, you add to the list. Oh, by the way, only God even has any testimony. So for those out there who would say, your theory is no better than that of the flying spaghetti monster, I will turn to that individual right at this point and I will say, I don't believe the flying spaghetti monster. You do! And I never get a disagreement at that point. I wonder why. It's not the creationists who believe in a flying spaghetti monster, it's the evolutionists who do. I like to turn the tables whenever I can. I think this is an excellent example. We can also rearrange the blocks a bit to form a water flow diagram. This will make things perhaps a little bit more logical if you want to study it to at least familiarize yourself with the arguments, if not go ahead and then try to produce them for other people. The first thing I'll ask is, does the universe exist? Well, yes, otherwise you belong in an insane asylum. All right? So since it does the universe have a cause? If you answer no, it's not scientific anymore. Therefore, we'll assume yes. Is that cause material or immaterial? Well, if it's material, then we go through the arguments we did before. Did the universe always exist? No. Otherwise, it would violate the second law of thermodynamics. Did the universe cause itself to exist? No, because otherwise it would violate logic. And then we're left with the immaterial choices that we saw earlier. It's a nice little flow chart, and it's powerful stuff, too. The pretzel logic that an evolutionist has to go through when being confronted by this, if he wishes to maintain his position, it's quite compelling. Paul might have very well used this on Mars Hill if things had been around like this back then. Next topic, how can the universe avoid heat death? Well, heat death, first of all, is what happens when the energy becomes less and less useful all the time. Well, according to Le Chatelier's principle, things will continue to get this less and less useful until there won't be anything left that is useful, in which case there will be no motion that is useful. Nothing will occur. Everything will be static, or if you like, in equilibrium. There won't be any dynamics going on. This is what we call heat death. And there is no way of avoiding this issue according to the laws of thermodynamics. And ever after that point, the universe will be fully deteriorated. Is there any hope of a constant or steady state universe? Well, I see things like that, but we come back to this business about the new science better agree with the old science, and the old science is the thermodynamics are still there. How can any material travel faster than the speed of light? Well, maybe you thought that there couldn't be any. Well, those who involve themselves in a Big Bang have a problem, because there's this thing called background radiation. Has an ambient temperature, if I understand, about 2.7 degrees Kelvin. The universe is already believed to be at 2.7 degrees Kelvin in outer space everywhere already. And the only way of avoiding a problem like that is to assume that there is at one singular point in time, if you're going with the Big Bang scenario, a hyperinflation. That is, where everything became moving much, 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 much faster than the speed of light, at only that one instant. And they say it's 10 to the minus 31 seconds. Well, how do we know? How could anybody really know that that's the case? How could anybody say 10 to the minus 31 seconds? Why not 10 to the minus 32 seconds? Why not 10 to the minus 30 seconds? Observation is failing at this point. And why only one time? Why not have a bunch of them? Why say that there was only one in the past and not others in the past? How can you have any confidence in anything if you're going to say a singular event occurred in the past with no repeatability? I asked Hugh Ross's reasons to believe in somewhat protracted detail some time ago about this issue, and they have no answer to it. They have no answer to why they should have to assume things like this, although they do. And they also have no issue for the next one. No answer to the next issue, and that is, what's the origin, transportation, and distribution of carbon?
Can you go back a slide for a moment?
Sure can.
And Hugh Ross, can you explain who he is?
Okay.
He's an evolutionist?
Hugh Ross is an old Earth creationist.
Old Earth creation.
Yes. He has a group called Reasons to Believe, which is on Arrow Highway east of Pasadena. Been around for about a generation now. He's 67 years old, as I recall, born in 1945, July 24, and he got his degrees in Canada. He's been highly involved with the stuff that goes on in JPL rather. But he holds to an old Earth creationist, that is, he holds that there's the flood is local, that there are long ages of Big Bang, and so forth. So in other words, he subscribes to a lot of what the evolutionist says, but he makes the distinction that animals couldn't have evolved. He does, however, subscribe that there was animal death before the fall in the Garden of Eden, which is another set of problems. So that's some of Hugh Ross. Come back to the matter of carbon now. This book describes that there are problems in trying to create carbon in the first place. If you're trying to use it by, you're trying to create it by one increment of atomic weight. That is, you go from hydrogen to helium to lithium, there's a problem, and that is, how do you get beyond this point much? Carbon has an atomic weight of 12. So the theory goes that we start off with hydrogen in stars. Who knows how they formed? We'll get to that in a moment. The hydrogen fuses to become helium, which has an atomic weight of 4. Now, there's a natural barrier in atomic weight 8 when you try to combine those two together. You'll get only a transitory species. So before the 10 to the minus 15 seconds occur, by which they could fall apart, a third one joins the group to form atomic weight 12 for carbon. That is an extremely improbable reaction. Not impossible, but improbable. It can only take place at one nuclear resonance, only in red giant stars, and can be disseminated only by a supernova. By the way, as I get to ask here, this slide, by the way, shows some examples of carbon. Could I have some answers from the audience? What examples of carbon do I see? Or not see? Anybody?
Diamond?
Huh?
What do you mean, diamond?
Sure, diamond's one. What's another one? The coal.
Coal.
Right. Anything else?
The earth.
I don't know about the Earth itself, but anything else? What that green stuff?
Gia.
Huh?
No.
Flat matter, right? Anything else?
Air,
What in the air?
carbon dioxide,
Carbon dioxide. Anything else? How about carbon monoxide? How about methane? There are all sorts of chemicals that have carbon in them. My question isn't the carbon, but how did it get here? I'd like to focus, if you like, on the fact that we have miles deep, thousands of miles long, solid coal beds. Miles deep, thousands of miles long, solid coal beds. How are we going to get this granular carbon that supposedly came from a supernova to here? You ever seen anthracite coal? Pretty hard, isn't it? Granular carbon will only stick together at most. It won't compactify. It even has to compactify to form bituminous coal, let alone anthracite. I would propose to you that there really isn't any good explanation for that that's out there right now. That carbon is not going to just jet its way from a red giant star 33 to 40 light years away at minimum to come only to the Earth. It's going to spread all over the place in the case of it's a supernova. Talk about dark matter. That's the original dark matter if ever I heard it. I went through that. See? Next topic. How do we get any stars to form in the first place? We need a star in order to have any of that hydrogen to form the helium, to form the carbon. How do we get any stars in the first place? Suppose we start off with a Big Bang. What's going to happen to the material that comes out of a Big Bang? According to Newton's laws, the first law says what? That something that is in motion tends to stay in motion. That something that is at rest tends to stay at rest. We know this from observation. We have no counterexamples to this principle. So what will the particles do if they're expanding outward? What will happen to them? They'll keep going and going and going and never stop going. To get a star, we have to have compression of a gas. We have to have them coming in together. Now, how do we expect to get compression of a gas when the only means that we have, even of compressing gases now, is to have a specific device surrounding a container? There are no such things surrounding a volume as big as a star, even a small star, out there. Are we going to expect that the particles are going to come together of their own when they're going the other way? This is one of those basic laws that I propose to you, just never gets around to being answered. And if somebody claims that there's some scenario, I'm going to ask them silly questions. How do you know it's true? Where did you get those ideas from? Do you have testable, verifiable, observable, scientific results in the questioning eye of the skeptic? Produce them then, please. I haven't seen them yet. I haven't heard of anybody else who's seen them. But if you want to come up with them, so there shouldn't be any stars. However, it's been estimated that there are 10 to the 21 stars out there. I don't know how they come to that number, but let's suppose it's true. And let's even assume that you give a generous 20 billion years for the age of the universe. This is far bigger than even Hugh Ross would imagine. Normally they say something like 13.7 billion years. How many stars on average per year would that mean that you'd have to form in 20 billion years? 50 billion stars every single year for 20 billion years. We get happy enough if we just see one. One of those little pillars like that. Have you heard the media saying that we have found 50 billion stars in the last year? Now this is, by the way, on average. You could be saying that maybe they all formed much further in the past and that we're going downhill from there or we're going up. The point is it's an average of 50 billion per year. I don't remember hearing anything about that in the media. Have you? 50 billion per year?
No.
No. As a matter of fact, the very notion of even producing one would pale in comparison to the 50 billion. Who would care about just one? I have fun with this one. How do moons form? Suppose you even have those stars and those planets that are circling around them. I've got a silly question to ask. How do you get solid moons around gaseous planets by blasting those planets? The gaseous planets, Jupiter, Saturn, Uranus, Neptune, how do you get a solid moon around them from blasting it? I don't know of any way means to get so, and even if you assume a nebular hypothesis, that is, the things were forming all at the same time, it still doesn't give explanation as to why the planets ended up being gaseous and the moons didn't. But we have a moon too. How did it form? Okay, there's a couple of things that might come to mind. One of them is to blast the Earth with a large enough object. Maybe a moon-sized object. Where? Maybe the Pacific Ocean region? Without an ocean, of course, because if you blast an ocean out of there, then you'll have to explain why there's no ocean up there on the moon. Very well, no ocean. What will happen to the particles when you blast them? The first thing they encounter, besides gravity, they have to escape gravity too, is Roche's limit. Now, Roche's limit is about 1 to 2% away from the Earth, and it's involved with something that's called tidal forces. If you can't get the particles beyond that point, then they will also fall back to the Earth, and there goes your moon experiment. Very well. Let's suppose that you even got the particles to go beyond Roche's limit, and that you actually got them to form something out there. All you'll get is an aggregate of particles. Any more than an aggregate of carbon particles will not form bituminous coal or even anthracite coal. But what does our own moon exhibit? It's a solid object. It's not made of a bunch of granules that have been sticking together. Otherwise, we wouldn't be able to land men on that moon. Or anything else on that moon, for that matter. Not only that, but to have an orbit would be to say that it doesn't just fly off into space, escaping with escape velocity away from the Earth. Otherwise, it'll just keep receding and receding and receding away from the Earth. We'd never see it again. Or it hasn't yet reached that, in which case it would fall back to the Earth anyway. No, you have to have another ingredient. It's called tangential velocity. That's a perpendicular force to the one that it's emerging from the Earth, so that it can actually orbit. It has to be going at just the right speed outward, as well as have the right amount of tangential velocity imparted to it from who knows where, mind you. There's no object that exhibits this. Impacting it so that it will form an orbit. And not only any orbit, but the orbit that we see. If the particles are coming out of the Earth, and there's a tangential velocity imparted to it, how often should that moon be orbiting the Earth? Once a day. If it's coming straight out of the Earth, it's hovering over the Earth turns once a day, so will the moon going around. How fast does the moon really go around the Earth? Anybody? How fast?
24 hours.
How fast does the moon go around the Earth?
Month.
Huh?
A month.
Yeah, or you'd say a month. That's how we got our name. Once a month. That, in other words, we have something that disagrees with known observation. We would expect it to be going around the Earth once a day if it came straight out. But it doesn't. It goes around the Earth once a month. How does anybody explain that? You got me. There's another object that we have to consider here, and that is the capture theory. That is, we have a large body, like the size of the moon, and it happens to come within range so that it is captured by the gravity. Well, I understand that's so coincidental nowadays that even the evolutionists have abandoned the idea. But for those who haven't yet, I've got other questions, like how come we don't see examples of other tribes? Other objects, maybe hitting the Earth, maybe going within Roche's limit. How come no examples whatsoever, not just around the Earth, but anywhere else for that matter, of other objects that failed to make an orbit? I don't see any at all. By the way, recently we've even had meteorites come in and we're scared by them. Witness the events that occurred last year. Think what would happen if you saw a moon coming in your direction. Since tidal forces overwhelm the gravity that might hold the satellite together within the Roche limit, catch this, no large satellite can gravitationally coalesce out of smaller particles within that limit. That's in Wikipedia. That's that whole idea. They don't just have to stick together, they have to compactify. And they have to escape beyond Roche's limit, or otherwise they'll fall back. What is the ongoing source of comets? This topic received a lot of attention on my third go-around in the Q&A session that followed. I don't know why, but it did. There are two kinds of comets. Short-term comets, which are said to have an orbital period of less than or equal to 200 years, like Halley's Comet, and they might be explained by the Kuiper Belt or by an interplanetary disk. There are also long-term comets which have a period that's bigger than that. Some of them might be explained by one of those devices, and some of them might not. It's the remainder that are the problem. And for this, the Oort cloud was hypothesized. That's spelled O-O-R-T. And what might you ask, is it Oort cloud? Let's just say it's like an automatic picture of dirty snowballs. Conveniently, of course, to make up for the comets that are lost in the sun, lose their mass, or otherwise dissipated. Nobody has ever seen the Oort cloud. People might have an idea, a starting point, a hypothesis of what that might look like, some evidence maybe that might suggest it, but nobody's actually identified to say, okay, there's our Oort cloud, and it's the body responsible for producing those long-term comets. Nobody's done that. But I'm an empiricist. If you show me a good Oort cloud, off the list it comes. Simple as that. This is a topic I have never seen anybody describe at all. How do any elements heavier than iron exist? In the same year that I took that education class, I also took a modern physics class and bought this textbook. And in chapter 9 of this book, I will not turn to it, is a graph called the average binding energy per nucleon curve. It's a curve that looks roughly like this as it goes down. And it peaks right around iron, atomic weight 55. Iron is predominantly atomic weight 56. Which means that everything heavier than iron, cobalt, nickel, copper, zinc, all the way up to uranium, every one of those elements is not as favored to form as iron is. How do they form at all then? That's the question that almost never gets answered. It's usually papered over by saying they formed in a supernova. But they never bother to answer questions like, what happens to those elements that are spread by the supernova? It'll be the same problem as with carbon. That is, they'll be distributed all over the place. They won't compactify together to form ores, O-R-E-S. In other words, they will not be economically mineable. You won't be able to get any cobalt, nickel, copper, zinc, uranium, anything else in economically viable proportion, or portions rather, to use. It'll just be scattered. It won't be of any use at all. That's not what we see. We see instead deposits occurring, certainly on the Earth. how do peptide bonds form? That same year that I took the education class and the modern physics class, I also took a biochemistry class. And on page 14 of this book shows the matter of forming peptide bonds. It also goes into the matter of what kinds of amino acids they have to be. I'll get to that in the next topic. These are models of amino acids. I'll point out the salient features to you. This is the central carbon atom. I have two of them, two identical ones here. This is the central carbon atom. This on the top is a hydrogen atom. The red represents a functional group, which can be either hydrogen or any of 19 other groups. The green with the two out here symbolizes the amine group. Think ammonia. And the other portions, we see a carbon, double bond to an oxygen and a hydrogen. This is called a carboxylic acid group. So in other words, we have a base and an acid in the same molecule. If you think about a carboxylic acid, you might think about those crazy ants that are displacing the red ants in the south because they cover their entire bodies in formic acid, which is the simplest form of a carboxylic acid there is. The structure, therefore, is NHCHCO. NHCHCO. That's the way they form. Now, when I combine these two, I will take one part from the amine group and one part from the carboxylic acid group. Join them together. Like so. That'll be what will form our structure. Notice what happened. A water molecule dropped out. Have you ever heard that explanation that we came from a warm little pond? Just how is that going to occur when a water molecule must drop out, not be absorbed by the amino acids? This is a problem. Okay, so there wasn't a warm little pond. We have a few other problems that come to mind too. If we have an oxidizing atmosphere, the oxygen will come along and destroy the amino acid bonds and maybe carry along with them the amino acids themselves. If on the other hand we don't have any oxygen, we have a reducing atmosphere, then we have no ozone layer and the UV rays come in and they destroy the amino acids and or their bonds. This is a chicken and egg problem. By the way, you know which came first, the chicken or the egg? Anybody want to venture a guess on that one? Which came first, the chicken or the egg?
Chicken.
God. But of the two, a hen and a rooster came first. It wasn't Adam and Steve Rooster, and it wasn't even Guinevere Hen, it was Adam and Eve Chicken. If you don't have any peptide bonds being formed, that's the structure I was forming here, it's called a peptide bond, then you have no proteins, you have no enzymes, you have no life whatsoever. In other words, this is vital. But it can't occur in water. And it can't occur, and it cannot occur in the environment at all. Instead, it has to occur in an existing body that wicks away the water so that it doesn't cause a problem with the reaction. This is one of many, many, many problems that occur in biochemistry. And by the way, without biochemistry, it's amino world. In case you wanted a bad pun for this morning.
David, can you go back a page again, please?
Sure.
just a moment?
Yes,
Okay, thank you.
any question?
So, by the way, is that the only thing that drops out, is the molecule, the water molecule itself?
In the end reaction, yes,
Okay, just for that reaction.
yeah. But it's the fact that the water molecule drops out that causes the problem for the evolutionists. Now, I mentioned to you something about left-handed and right-handed. I need to exchange two of these bonds to get the point across. So in other words, I have broken the bond momentarily for the sake of the presentation. Let's see. Turn this in such a way. That'll be close enough, I guess. Okay. I'd like you to take a look at these amino acids now that I have changed the bond. Can you see that one of them is a mirror image reflection of the other? Can you see that? In other words, there's the carbon, and I didn't put that together. Oh yeah, there it is. There's the amine group up there, and there's the carbon with its functional group, and the hydrogen, and the carboxylic acid bottom. Can you see that those are mirror images of each other? Can you see that? Just like in that diagram, 1.2 here. That one? See, those are two mirror images. Can you see that being demonstrated in 3D right here? Look at that. Okay. There is, however, no way to stick one on top of the other so that they all will match. The most you can hope for, besides the carbon itself, is 2 out of 4. Meaning they're what we call non-superimposable. These are actually different molecules. They have the same melting point, boiling point, refractive index, vapor pressure, chemical reactivity, density. They have all the same environmental properties one does to the other. The only way you can separate them from each other without combining them with other compounds is under plane polarized light. One will turn plane polarized light this many degrees in one direction, and the other will turn the same number of degrees in the other direction. That's how you can tell them apart by themselves. But otherwise, they're indistinguishable. That also means they have the equal probability of being formed in the first place. If you start with neutral ingredients, a neutral environment, neutral energy sources. So how do we get only left-handed amino acids in proteins? And for that matter, the sugars are almost all right-handed too. Isaac Asimov, the famous atheist, tried to explain this in a long diatribe a number of years ago, and essentially the conclusion is, well, it just happened one way instead of the other. If Mr. Asimov were here, I would ask him a silly question. How did it happen that they all happen to be this way across the entire face of the globe? There isn't one single counterexample to it. And no, they don't replicate. This is what he was trying to propose. He ought to have known better than that if he's a scientist, to say such things. There are right-handed, that's dextrorotatory, that's right-handed, amino acids in other structures, like bacterial cell walls. That's to keep the enzymes, which are left-handed, from destroying the bacteria. And by the way, if bacteria do encounter amino acids, proteins, they're right-handed, they will disassemble them, turn them into left-handed, and digest them if in fact they can digest them at all. So it shows even the bacteria have a preference for left-handed amino acids even when presented with right-handed ones. This is a composite. What happens when I take the tetrahedra, which are the basis for an amino acid, and put them together, and you can see that they're embedded in a cube. And you can even measure the bond angle in the cube. This is an exercise that's done as a freshman in college. I wish they would put it in high schools too, because it's within their grasp. Working out the math using the law of cosines, the answer is the arc cosine of minus 1/3, which is approximately 109 degrees and 28 minutes 16 seconds. If things vary from that, then we can get an idea of what kind of an amino acid we have. That particular bond angle will be if you have an equal components from the carbon, like a methane molecule, or carbon tetrachloride, or carbon tetrafluoride, where they're all equal. If they're not, we can get an idea by the fact that bigger groups will stretch in that direction more than smaller groups will. I'd like to read a comment now from my organic chemistry textbook on page 236. It says something about those amino acids in the first place. This is a secular textbook. It has no axe to grind in a particular direction. Indeed, we deal with optically active substances to an extent that we may not realize. We eat optically active bread and optically active meat, live in houses, wear clothes, and read books made of optically active cellulose. The proteins that make up our muscles and other tissues, the glycogen in our liver and in our blood, the enzymes and hormones that enable us to grow, and that regulate our bodily processes, all these are optically active. Naturally occurring compounds are optically active because the enzymes that bring about their formation and also often the raw materials from which they are made are themselves optically active. By the way, optically active is just another way of saying they're left and right hand, or they're chiral compounds or stereoisomers. But listen to this quote. As to the origin of the optically active enzymes, we can only speculate. The situation is no better now than it was when this book was being written in 1972. The problem existed for more than a century before that. Yes?
How many new additions have there been to that, do you know?
I don't, but
Or do you know what the newest one says about it? Is it about the same?
As far as this particular book, you would have to say the same because it's a standard result. Nobody has disagreed with that, and and by the way, if anybody did produce an actual reason, not this speculative 300 and some page book that I read on the subject that went supposedly from the non-parity of particles up to that point. If anybody did, it would be an automatic Nobel Prize winner, I predict. People have been looking for that for a long, long time. Good luck. Also, I'd like to say about the tetrahedron and the cube in the first place, the very fact that there are only 5 Platonic solids, and those are 2 of them, I don't think that's any accident. I think that's an evidence of design. You be the judge of that we can embed the tetrahedron into the cube so perfectly. What turned non-life into life? Let's suppose that I give you a dead dog. Dead long enough, 3-4 days, whatever. Hercules, one small task. Breathe life into the dog. What's the matter, Hercules? Is this not a small task for you to perform? I've given you everything. I've given you the brain, the liver, the heart, the lungs, the muscles, the skeletal structure, the nervous system, the spleen. I've given all that to you. Aren't you Hercules? Aren't you able to do this? Well, maybe the task isn't so small after all. Now, I've got another silly question. If you can't breathe life into a dead dog, how do you expect to breathe life into materials made into a dead dog? And you're going to have a problem getting the dead dog in the first place if all you have to start with is hydrogen. There is no spontaneous generation. There is no hopeful monster, Goldschmidt or otherwise. All we've ever known is that life comes from life. This was established by Pasteur in the 1860s. That's all we've ever seen. And none of this business about RNA doing all the work. I've heard that one a few times, and that's still only a theory. You may think you're close, but you're nowhere close. How does metamorphosis occur? There are 2 kinds of metamorphosis. One of them is amphibian metamorphosis, and the other I'm going to mention a feature of it, and that is insect metamorphosis. Now, I could grant you that out of the 4 stages that we're familiar with, egg, larva, pupa, adult, I could perhaps grant you the adult laying the eggs, the eggs hatching into the larva, and the larva spinning a cocoon or other device around the pupa. But would somebody please tell me how that mushy stuff in the pupa, which has no control of its own destiny, turns into an adult? I have yet to see anybody even come up with something reasonably close, but I'm an empiricist. You biologists out there, you show me a good step-by-step, no guesswork procedure to get from one to the other, no, we'll start listening. How do major morphological changes occur? What are morphological changes in the first place? Well, morphology means to change, so it's kind of a duplicate word. It's what happens when you try to go from one kind to another. As in, a fish to an amphibian. You'd have to go from no metamorphosis to metamorphosis. The heart would have to go from 2-chamber to 3-chamber. If you go from an amphibian to a reptile, you'd have to go from metamorphosis back to no metamorphosis again. And also, the fertilization goes from external to internal. To go from a reptile to a bird, you have to go from cold-blooded to warm-blooded, and you have to go from scales to feathers. And if you want to go from bird to mammal, you have to go from wings to paws, hands, or hooves, and feathers to hair. And there are undoubtedly many other changes that would have to occur as well. You'd have to also have them true of both male and female, co-located to form a colony. And do we have any reasonable hypotheses for how all that could occur? I'm not going to say it's impossible. I mean, it did occur. I may have a different explanation of how it occurred. What creates information from gibberish? Communication, if you're familiar with it, requires a sender and a receiver tuned to each other with a medium between that promotes rather than inhibits communication. Well, first we'd have to explain, how did we get the sender? How did we get the receiver? How do we get them tuned to each other? And how do we get a suitable medium? I don't hear anybody come up with explanations for those either. And there's also a measure, I won't go into it here, a measure of how random things are to distinguish it from gibberish. It's called the autocorrelation function. That is, you can line up a sequence against itself. Suppose you have the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, we could make an autocorrelation measurement and show that there's virtually no chance of that occurring. On the other hand, if we mix them up, like 1, 8, 4, 2, 8, 1, 8, 4, 2, 6, 5, 7, well, there's probably more chance of that occurring just randomly. And there's even a glorification of it called the ambiguity function. And this is used in radars. Measures range against velocity. If you want to bury code, you do work in areas like this. And just as there is energy entropy that we were speaking of earlier, there's also a corresponding thing called information entropy. That is how scrambled information becomes. It's akin to the matter of heating gases. All life structures need information. For example, the DNA codes for the proteins. The proteins code for the DNA. How are you going to get one for the other and the other for the one if you've only got one to begin with? If you've even got one to begin with. You need information to convert one to the other. I'd like to read I'd like to mention something in this set of books, which is my last remaining copy of Flaws in the Theory of Evolution. In Chapter 2 is a section on mechanistic origins. There's a couple of interesting things to be said for this. One is, step after impossible step is begged in the course of these polemics. That's all these things amount to for those who are engaged in this field without taking on the science itself. It becomes nothing more than, as he put it, a sonneteer trying to write poetry in 14 lines. It doesn't have any usefulness as far as science is concerned. All it is just arguments. He also goes on to say earlier in that same chapter that if you're trying to form proteins by chance, you might be able to get with 1 or 2 or 3, but that's it. You won't get any more proteins than 3. This is a far cry from getting anything that we need. mention to you an answer to this. 16 scientists out of others that I could have pulled. Do you recognize those names by any chance? Some, maybe all of them? They're all in your modern mathematics, physics, and chemistry textbooks. What else did they have in common?
They were believers.
Not all of them were, but they weren't evolutionists. Some of them were, but most were not. I'd like to ask if anybody would like to have gone against any of these people in his chosen field in Jeopardy, Double Jeopardy, or Final Jeopardy with Alex Trebek at the helm. Do you think any one of us could have survived against any one of those people? I doubt it. And yet, we would say that these people are the foolish ones nowadays. You've got to be kidding me. Without these people, we would not have any modern science. These are the references that I was using implicitly or explicitly using in the talk. Only the ones in green are considered on the creationist side of it all. All the others are secular texts. In fact, that's what you'll find if reading David Schutz's Flaws in the Theory of Evolution. Every reference but one is a secular reference. Can't argue with science. It's all going to testify in the same direction, whichever way the truth goes. Does anybody have any remaining questions? I've put these 16 categories up in case, what is it, a refresher? Yes?
So you just barely touched on how proteins can be by chance duplicated.
Not by chance.
Right, well, no, I'm saying the evolutionists believe that can happen. by
They
chance.
believe it can, but I'm trying to show it's going to be quite impossible, or
Right.
nearly impossible, I should say.
And also, don't they, they believe that scientists can duplicate certain things, like even cause life, but they have to use a catalyst?